Okay, so again, thanks for the introduction. And so today I'll be talking about planar orthogonal polynomials. It is a product together with Alfredo and Cap McLaughlin and Nick Sim. And well, I guess a lot of us are familiar with orthogonal polynomials on the real line, but we will be talking about planar orthogonal polynomials. So there are polynomials that satisfy an orthogonality relation like this that you see here. So these are polynomials Pn of degree n and positive leading coefficient. And the orthogonality is with respect to a measure on the complex plane. So that's also why they are called planar orthogonal polynomials. And if this measure is so nice, let's say continuous, and well, it has a density which is continuous and positive, let's say, then we know that that such a sequence is well defined and unique. And our interest is to find out the large n behavior of such polynomials, and also to find out how their zeros behave. So okay, for the people that know a bit more about orthogonal polynomials, I should mention there are a few differences with orthogonality on the real line. For example, in general, for planar orthogonal polynomials, there is no three-term recurrence relation. There is no Christoffel-Darboux formula, and some of the standard strategies to get the larger behavior of the polynomials that work for orthogonality on the real line do not work for planar orthogonality. For example, there is no Riemann-Hilbert characterization, at least not initially. So there are a few classes that we understand quite well. First of all, there are some rare cases where the planar orthogonal polynomials are simply classical orthogonal polynomials, or semi-classical, I should maybe say. So there are examples with Amit, Gegenbauer, and generalized Laguerre polynomials. Then one situation that's trivial in a way is the situation of rotational symmetric weights. So in this case, this density I showed you before, this one is rotational symmetric, only depends on the modulus of z. And it's fairly easy then to see that that the orthogonal polynomials, the planar orthogonal polynomials, are just monomials. They're just z to the n times some leading coefficient. That's something you can easily see by going to polar coordinates in the integral that defines the orthogonality. But okay, something a bit less trivial is what Kahneman did. So one of the first works on planar orthogonal polynomials, I think you could ascribe to Kahneman. So he considered a weight, or well, a measure, that's a characteristic function with respect to some subset of the complex plane. So if this subset is assumed to be connected and it has a smooth boundary, then he proved this large n formula for the orthogonal polynomial. So I should explain a few things here. So here, phi is the map from the complement of the set A, or rather the closure of A, to the exterior of the closed unit disk. So we know that there is a conformal map like this, and with these normalization conditions that fixes what this map is, so that phi of infinity is infinity and the derivative should be positive. And I should mention that this holds on an open neighborhood of the exterior of A, so the complement of A. In particular, this asymptotic behavior doesn't tell you much about what happens strictly inside this set A. Okay, Now, more relating to what I will discuss is a different type of planar orthogonality. So here we consider exponentially varying weights. So they have the form e to the minus nv. Usually we call v the potential, and we assume that this v is sufficiently regular. Usually we assume that it's C2 and real analytic. There should also be a condition for how it behaves at infinity, such that the orthogonality is well defined. So quite recently, Hedemann and Venman proved a result similar to Karlemann's result, which is also valid in a certain region, but not in another region that we want to understand. I will explain this in more detail in a moment. But first, let me introduce some applications of well, in particular of these exponentially varying weights. So the main application is what we call random normal matrices. So it turns out that this measure, this exponentially varying measure, in some way it describes the eigenvalues of random normal matrices, so matrices M, which are distributed according to this expression here. Here Zn is some normalization constant. The trace you should interpret as the sum of V evaluated in the eigenvalues of your matrix. And d squared Mij is just the standard Lebesgue measure on the complex plane. So, well, these matrices are random. It also means that their eigenvalues are random. And so these eigenvalues can be described by a joint probability density function. So it turns out that if you consider these eigenvalues, let's call them Z1 up to Zn, then the corresponding joint probability density function is given by this expression here. This is a determinant of an n by n matrix, and the components of this n by n matrix are all constructed with the same function kn of two variables. Well, this function usually we call the correlation kernel. That's not so important. But what's important is that it is actually constructed with the planar orthogonal polynomials, right? The orthogonal polynomials with respect to this measure here. Right? Okay, so indirectly, these planar orthogonal polynomials describe the eigenvalues of random normal matrices. There is also another application, which is got what we call a Coulomb gas. So that's an application from physics. So these eigenvalues, they can also play the role of the locations of particles in a certain gas, which you call Coulomb gas, which satisfies certain two-dimensional electrostatic laws. So that's another application. And one thing that we will be interested in this talk is what we call a point charge insertion. So it turns out if you want to add a point charge to this Coulomb gas, that corresponds to adding a factor z minus x modulus to the power gamma in front of our weight, in front of our measure. Okay? So this factor, what it describes is a charge at location x, well, with some intensity that's determined by gamma, and physically that corresponds to a point charge insertion. And this, in general, makes the model harder to analyze if you have such a point charge insertion. Okay. So this will be one of our main focuses. Okay. But I also want to explain a little bit about these Coulomb gases or random normal matrices. So you see here that well, it has a determinantal structure, this joint probability density function, right? So that's okay when you are point process has a structure like this, we call it a determinantal point process. And there is something special about it, and you can see it in this picture here. So on the left, you see a random normal matrix model. This particular one we call a Geneva ensemble, and it corresponds to V is Z modulus squared. So you see this on the left, the eigenvalues of a matrix in that model. And then on the right, you see a configuration where points are uniformly distributed on the unit disk. And there are some notable changes that you can see. So if you look on the right, you see there's way more clustering. There are way more situations where points are close together. And on the left, you don't really see that. And there is a reason for that, and that's that there is a sort of built-in repulsion in these type of models. And that's because of this determinantal structure. So you can imagine if, for example, Z1 and Z2 are close to each other, then that means that the first and second column of this matrix are very similar, and that means that the determinant is close to 0, right? So the probability is close to 0. So there is a repulsion built into these systems. Okay. So before we talk more about this point charge insertion, let me tell you a little bit about what we know about random normal matrices or long gases. So under fairly general conditions, we know that the eigenvalues accumulate on some set, which I denote by SV. Usually we call it the droplet. And we can also see this already a little bit in this picture, right? So in the right picture, we just had a uniform distribution on the unit disk, so obviously it should be in the unit disk. But on the left, you also see that somehow these points, particles are contained in some region, it seems. There aren't many outliers. And it turns out that for this particular model, the Geneva ensemble, indeed, in the large n limit, all the eigenvalues will be on the unit disk. So in formulas, you can be a bit more explicit about this. So, well, you will have to believe me that it's a fact about determinantal point processes that if you take this function kn on the diagonal, so zz, and divide it by n, that gives you the average density of the eigenvalues. And when you take the large n limit of that object, you actually get a limit. So you get the Laplacian of the potential divided by 4 pi, and that's inside the droplet, strictly inside, in the interior. But outside the droplet, you get 0. So there, in the large n limit, you won't see eigenvalues anymore. Okay. Well, so the particular form of this limiting density is just the Laplacian of V. But in general, determining what SV is, so what the droplet is not an easy task. But it has a certain potential theoretic interpretation. So it's as follows. So we consider this functional that you see here. So it depends on V, and its input is any measure. And the problem is to minimize this over all measures mu. And then the measure that minimizes this is actually the one that has this density that you find here, and that has the support given by SV. Okay. So I mentioned before that there was this result by Heyman and Venman, and that I would be a bit more clear later on, and that's this point. So in their case, they get the following large n formula for the planar orthogonal polynomial. So again, there is a conformal map. This time it's from the exterior of the droplet to the exterior of the closed unit disk, again with a similar normalization as before. Then B is some holomorphic function. In their paper, they can be explicit about this, but I won't. Is it okay? It's a holomorphic function. And then this calligraphic V is the bounded holomorphic function such that its real part equals the potential on the boundary of the droplet. So I'm saying here under fairly general conditions, in particular, they do assume that the droplet boundary is smooth. But again, just as in Karlemann's result, this only holds for Z in an open neighborhood of the exterior of the droplet. In particular, when you're strictly inside the droplet, not many general results are known. And it's actually the interesting region in a way, because that's usually where that is where the zeros of the planar orthogonal polynomials will be. So exactly in the region that you can't see in this expansion. Okay. So so the interesting question is, well, what does happen strictly inside the droplet then? And we can go even a step further, which is our focus. What if we also add a point charge insertion? So that's a difficult question that doesn't really have a general answer. So the answer is, in general, we don't know. But there is some approach in specific models where you can actually find out. And the idea is essentially that you start with a model that you understand well. For example, a model that has rotational symmetry. Then you add a point charge to it, and then you study that. And the advantage of that is that a lot of behaviors of the model without the point charge insertion are still valid. For example, the droplet is still the same if you add a point charge insertion. And the limiting density of the average number of points is also the same. So this is exactly what several researchers did for the Geneva ensemble. So the Geneva ensemble is a prototypical example of a random normal matrix model, although sometimes they leave out the normality condition, but that's not essential. So here we take the following weight, so a Gaussian weight, and the potential, so that means that the potential is modulus Z squared. And as I already mentioned before, if you have a rotational symmetric model, then the planar orthogonal polynomials are just monomials with some leading coefficient. And for the Geneva ensemble, you can determine these explicitly. So these are the coefficients you find. And that means that the corresponding function Kn, the kernel, takes this form here. So it's very explicit in this case. Furthermore, I also mentioned this already when we viewed the picture. We know that the eigenvalues of the Geneva ensemble, that is a matrix sampled from the Geneva ensemble, they will accumulate on the unit disk in the large n limit. So the question then is, okay, so what then happens if we add a point charge insertion? Without the point charge insertion, the situation is more or less trivial. We know that the zeros, for example, are just at Z is 0, the zeros of the polynomial. But when you start adding a point charge, actually the zeros change. So this was treated by Balog, Grava, and Merzi, and by Li and Yang. I'm using here the archive years. I think actually the paper the first paper was published in 2017 and the second in 2016. But I think the first one with Balog, Grava, and Merzi was actually a little bit earlier on the archive than the paper by Li and Yang. So what they proved, I will show in the form that Li and Yang presented. So in the case of the Geneva ensemble with a point charge insertion, they get the following result. I should also explain, because of rotational symmetry, this location of the point charge can be assumed to be positive. or 0. Okay. So I will only tell you what happens when x is inside the droplet, so inside the unit disk. They also proved it outside the unit disk, but okay, I will focus just on the inside. And okay, this parameter gamma should be bigger than -2 and non-zero. And then they consider a certain curve, which is important. So they have this curve here, which is essentially a level curve. So it's determined by this condition here that you see. And their result uses a thin neighborhood of this curve. So before I dive into the formulas, let me show you what this curve looks like. So it looks like this. You see it in the you see it in the left picture over here. And as you might guess, the dots are actually the zeros of the orthogonal polynomial. And I will now explain why that is the case, why this curve gamma is attracting the zeros. So what they could prove is if you look at the exterior of this curve, but not too close to the curve, so it's somewhere in the exterior, not too close because you have to stay outside of U, this thin neighborhood of the curve, which is not, which you don't see in this graphic here, but you should imagine some thin neighborhood of this curve. And if you're in the exterior, then they find this behavior here. And if on the other hand you're in the interior, so you're in this region, but not too close to the curve, so not in the thin neighborhood U, then they find this expression here. Now it's not so important what these expressions are exactly, but the important thing is that this expression can't be 0, and this expression also can't be 0. So Z0 is not part of the exterior of gamma, right? So then there is only one conclusion. If our orthogonal polynomial does have a 0, it has to be in this thin neighborhood U of the curve, right? So that's exactly why when you plot the zeros, they are attracted by this curve. They're not exactly on this curve, so this is a zoom in the right picture. Actually, Li and Yang showed that the zeros are on a slightly different curve that in the larger limit will become the red curve. Yeah. Also, if you do have a 0 of P, then that means that z to the n should be of the same order as e to the n x z minus x, right? If you think about that for a moment, that's actually exactly this condition that you see here. Okay. Well, then they also showed some interesting behavior near the point insertion. So in a small neighborhood of x, they can show some special function type behavior. Okay, maybe one thing I should have mentioned is capital P just stands for the monic orthogonal polynomial. You just divide it by the leading coefficient to get the monic orthogonal polynomial. Okay. Yes. Yeah, as I mentioned before, so they also investigated the cases where the point insertion is outside of the droplet or on the droplet boundary or close to the droplet boundary. I will not. Okay, I will omit these details, but they also did that. You might also wonder, well, if you can do one point charge insertion, can you do more? And that indeed has also been done. So by Li and Yang in 2020, and also by Beers-Para and Arno Kuilers. But in this talk, we will only focus on one point charge insertion. So far, I've shown you the results on the orthogonal polynomials, but as As I told you, there's also a random matrix or Coulomb gas interpretation. So what can we say there? Well, the eigenvalues are essentially encoded by this kernel Kn, and this is actually quite well understood. Even though the planar orthogonal polynomials are not entirely well understood in certain regions, the kernel actually is quite well understood. There is in more or less everywhere in the complex plane. But there are other things that you can investigate. So what we investigate and what others have done before us is the moment of characteristic polynomials. So you consider a matrix sampled from a Geneva ensemble. So that was the one where V is Z moduli squared. Right? And then you consider a moment that is the expectation value of some power of the modulus of the characteristic polynomial. It doesn't necessarily have to be integer. You can also consider real or even complex values for gamma. Explicitly that's given by this formula that you see here, which is sometimes also called the partition function. Okay, so for the Geneva ensemble with point charge insertion, this was treated by Webb and Wong. So they showed how the moment of the characteristic polynomial behave as n tends to infinity. The result is as follows. So they take the characteristic polynomial of a matrix sampled from the Geneva ensemble to some power gamma, and then the expectation value, and then the large n formula that they find is this formula that you see here, and this g here is the so-called Barnes g function. So it's defined as follows, and one of its defining properties is that it satisfies this functional equation. So this gamma here is the gamma function. Okay, then there's also a corollary of this. So this is essentially this expression, the moment of the characteristic polynomial is essentially the moment generating function for this random variable, namely the logarithm of the modulus of the characteristic polynomial. And it turns out if you center it properly by this term here and rescale it, then you can show that in distribution, this will converge to the standard normal distribution. Okay, so far these are results that were already known. So now I will tell you what model we were investigating. So we can't do anything too general, so we had one specific model. Maybe before I continue, are there any questions so far? If not, then I will continue. Okay, so we consider the following model. So we have planar orthogonality, but in our case, it's actually on the unit disk. And the explicit measure that we are investigating is this one that you see here. So it also has a point charge insertion built into it, right? The c minus x to the gamma term. Now, if you don't have this point charge insertion, but just this term, then it turns out to describe a particular random matrix model. Actually, not a random normal matrix model, but it's the so-called model of truncated unitary matrices. Well, without going too much in detail, there is a way to hard distribute complex unitary matrices, meaning there is some measure that's invariant on the left and right multiplication, which exists, and For these type of random matrix models, we know that the eigenvalues live on the unit circle. But if you start taking a sublog of such a matrix, so UN here stands for the higher distributed unitary matrix, which is a capital N times capital N matrix. But now we consider some upper left subblock Pn, where n is some number smaller than capital N. And we call Bn a truncated unitary matrix. And in the case of Bn, actually the eigenvalues do not live on the unit circle, but they live on the unit disk. And then it turns out that if you look at the eigenvalues of such a truncated unitary matrix, which are random then they are distributed according to this probability density function that you see here. This factor is it's a van der Monde factor, and I hope people know what that is, but okay, it's some factor. But here you have the measure that I defined here, but without the point charge insertion. And if alpha is taken to be capital N minus n, then that describes the truncated unitary matrices, or rather their eigenvalues. Okay. And it's also a determinant of point process, but in this case on the unit disk. So, well, you have some options for this parameter alpha. It basically tells you how big your subblock is. And our main focus is the case where capital N and N are proportional to each other. So they both they both grow with n, well, either one of the n's. And what we assume is the following. This is often called the strong non-unitarity regime. And we assume that n divided by capital N is, well, in the large n limit is equal to some proportional number c, which is between 0 and 1. And well, that means that alpha, so this alpha that we have here, it can be seen as some constant times n. In particular, it grows with n. And in that case, you can show that the eigenvalues accumulate on a set which is smaller than the unit disk. So remember, the truncated unitary matrices have eigenvalues in the unit disk. But if you take this condition for alpha, then actually the eigenvalues accumulate on a smaller disk, which has radius square root c. And and we will only consider the case where our point insertion is well, in the bulk, as we call that, or it's strictly inside the droplet. So and again, by rotational symmetry, you may then assume that it is in this interval of positive numbers between 0 and square root n. And in some sense, from the perspective of the eigenvalues, you could say that that this corresponds to a random normal matrix model. I mean, the truncated unitary matrices clearly are generated in a different way than the random normal matrices. And also, they're not normal in general. But if you purely focus on the eigenvalues, you can describe this in the same way as a random normal matrix model. So then you have to take the following potential that you see here. And well, you have to let it equal infinity outside the unit disk. And then by exactly the same arguments before, you can show that this is a determinantal point process with some kernel Kn that you see here, which in particular is constructed with the planar orthogonal polynomials of the weight of this weight here. Okay, so yeah, so we are basically interested in the the three different types of results I showed you, the result by Li and Yang and Balogh, Grava, and Merzi, and the results by Webb and Wong. And we want to prove the analogous results. So in particular, we want to understand the orthogonal polynomials. And we want to understand the moments of the characteristic polynomial. In this case, the characteristic polynomial of the truncated unitary matrix. Okay, I already said this before for the Geneva ensemble. So this has the interpretation of the moment generating function of this random variable, which we want to understand. We want to prove some central limit theorem for this object. So let's first look at the orthogonal polynomials. Here we have a sort of similar situation. There's again a curve that attracts the zeros, or sometimes called the skeleton. In this case, this curve gamma is given by x times gamma 1. So all the elements in gamma 1 you multiply by x. And gamma 1 is defined via this condition. So again, it's a curve that's defined as a level curve. And in this case, the function that's being used for that is this function here, phi of z, which is the sum of two logarithms of this type that you see here. And you can already see in this simulation here that indeed the zeros which are plotted here, I think this is for NS25 if I'm not mistaken, that they are attracted by this curve on the left. This curve on the right, by the way, is part of the same level curve, but we're only considering the curve on the left. That's the one that attracts the zeros. Okay, so let's see if we can put this in formulas. So this is our first result. So we again consider some thin neighborhood of this curve gamma. We consider the monic orthogonal polynomials, so with leading coefficient 1. And we consider the regime of strong non-unitarity, so alpha is of this form here. And then in the larger limit, we get the following behaviors. So if we're in the exterior of gamma, so we're outside of gamma, but not too close because we are not supposed to be in the thin neighborhood U, then we get this behavior here. This is exactly the same as in the result by Li and Yang. Now, if we're in the interior of this curve, but not too close to the curve itself, so outside of the thin neighborhood U, then we have this behavior here. And again, with both these behaviors, we can see that that these expressions actually can't become zero. So the only conclusion then is that the zeros of the orthogonal polynomial have to be in this thin neighborhood U of the curve gamma. And if you do have a zero, then z to the n should be of the same order as, x to the n times this factor here to the power alpha plus gamma over 2. Remember that alpha is actually some constant times n. And if you think about this, that gives you exactly this level curve here. Then also here, there is some interesting behavior near the point charge insertion itself, so near x. So there we get some expression in terms of the upper incomplete gamma function. Okay, so that's the result for the orthogonal polynomials. Let's now look at the moment of the characteristic polynomials. So again, we consider the strong regime of strong non-unitarity. And here we get behavior that's quite similar to the result by Webb and Wong. So it's quite similar. We even also get the Barnes G function in our result. Okay, so then there is also a corollary for the logarithm of the modulus of the characteristic polynomial. So here we find the result quite similar to weapon 1 again. But to center this expression, we have to use something else. We have to use a different expression. So we have to use this expression here. But we again have to rescale with the same with the same expression here. And then we also find a central limit theorem. So we show that in distribution we get the standard normal distribution. Okay. Okay, so those are the results. Let's see how much time I have left. Yeah. So let me tell you a little bit about how we proved these results. So a big step in the proof is some trick that was used in Li and Yang, and I believe also in Grava, Balog, and Merzi, which is to somehow reduce the planar orthogonality to orthogonality on a contour. In other words, the two-dimensional orthogonality becomes a one-dimensional orthogonality. So this can be proved with an argument involving Green's theorem that I'll get to in a moment. So there is a lemma that we prove. Well, we rescale our polynomial. That's okay. That's for convenience. It's not really essential. And then we can show that the planar orthogonal polynomials, so these actually satisfy a certain orthogonality on a contour, some contour C, where C is any contour around the interval from 0 to 1 that doesn't intersect the interval from 1 over x squared to infinity. And this weight Wn is defined like this. You might notice something important about this weight, which is that it's actually analytic. So that also means that you have some freedom in deforming this this closed loop, which is indeed what we use in our proof. Well, okay, this chi j is related to the leading order coefficient. So let me sketch how this works. So we start by using defining some auxiliary function you see here, and the original planar orthogonality is actually equivalent to what you see here in the first line. So in the original orthogonality, instead of z minus x to the k here, you would actually have pk. You would have the polynomial pk. But when you think about it, this is actually equivalent to consider a term like this. Now, the point is, if we take the derivative with respect to z bar of this function here, I see I forgot the k here. What do you get then? Well, by just the fundamental theorem of calculus, if you take the derivative with respect to z bar, you get the integrand that you have here, where you have to plug in s is z bar everywhere. So you get z bar minus x here, and here you get 1 minus z modulus squared. Right? So if you put that in this place over here, you'll see that you get exactly this expression in the first line. Right? Now this d over dz bar, you can actually put in front of the entire integrand, because this part of the integrand depends on z, but not on z bar. And then Green's theorem tells us that actually that's equal to an integral over the boundary of the unit disk. And that's how you get here. And then, the last steps are to show via some algebraic manipulations that actually this auxiliary function has a nice form when z is on the unit disk. And this, this is already quite similar to this weight that you see here. You still have to do this rescaling of the polynomial, but then you'll see that you get this weight that you have here. Okay. Now you might say, okay, that's nice. You have reduced the planar orthogonality to orthogonality on a contour, but how does this help you? Well, this helps you because when you have orthogonality on a contour, actually there is a Riemann-Hilbert problem associated to that. So Riemann-Hilbert problem is something of the following form. It asks for a function, in our case, a 2x2 matrix-valued function, which should be analytic outside of this contour C that we had before, right? On which we have the orthogonality. Then on C, it's not analytic or even continuous, but it does have continuous boundary values if you approach the contour from the inside, which is the plus side, or if you approach the contour from the outside, which is the minus here. And then these two limits are related to each other by this matrix multiplication. This matrix is usually called the jump matrix. And we also want y to have a certain behavior as z tends to infinity, which you see here. And then it's well known that that this Riemann-Hilbert problem has a unique solution that you see over here, and in particular, it has our orthogonal polynomial, right? So here the chi n is actually the leading coefficient. So actually, this will give you the monic orthogonal polynomial. So the thing is, if we understand the large n behavior of y, then we also understand the large n behavior of the orthogonal polynomial, right? Now there is also another polynomial qn in here, which I could give you explicitly, but I won't. But okay, there is some auxiliary polynomial that you need in this construction. And it's not just that understanding the large n behavior of y gives us the large n behavior of the orthogonal polynomial, because we can also say something for the moment of the characteristic polynomial. So we showed that a certain differential identity holds. So if we look at the log of the moment of the characteristic polynomial, and we differentiate with respect to the x, the location of the point insertion, then it turns out that we have a formula like this. And what's important to note is that every expression that you see here, so the qn or the p tilde n, etc., they are all in this solution y. Everything you need is in the solution y. So if you understand the large n behavior of y, you also understand the large n behavior of the moment of the characteristic polynomial. Well, okay, the derivative of this, I mean, you have to do some work, but yes. Now, there is basically a standard way, well, more or less standard way to solve such a Riemann-Hilbert problem. By solve, I mean asymptotically solve it, so understanding what happens as n tends to infinity. So this is known as the Deift-Zhou method of nonlinear steepest descent. It consists of a series of transformations that transforms the original Riemann-Hilbert problem to a new Riemann-Hilbert problem, until finally you are at some final Riemann-Hilbert problem for, well, I'm calling it R here, that in some sense is simple enough to understand the large n behavior. And then once you have the large n behavior of the final transformation of R, you can actually invert all these transformations and then find out what that means for the large n behavior of y. So in our case, we can show that after the final transformation, this R has a particularly nice form. You will have to excuse me for this weird notation, but it didn't fit on the slide otherwise. So this e to the n phi tilde s is actually this term here. And this phi s is the same function from before. It's a function that determines the curve gamma, right? This level curve that attracts the zeros. And one can argue that this term here, with the O term, that's small. So it's really this matrix here that gives the dominant behavior of R. And well, for the few experts, maybe I would mention that we somehow are able to avoid having to construct any local parametrices. So instead, we have some small norm argument where we use the explicit structure of the jump matrix of R and are able to find this result here. So these are in the off-diagonal elements. You see contour integrals over certain curves, which are related to this curve gamma that I showed you before. But for that curve, you would have to take r as 1 here. But these curves here are for well, different numbers, so numbers r1 and r2 that are bigger than 1. But if you look at these integrands, you see that actually they are analytic, at least outside certain intervals, and so you have some freedom to deform these contours, and that helps you. So for this integral here over the curve gamma r2, you can actually pass it through a saddle point. So that's this integral here. You can pass it through the saddle point of phi. It only has one saddle point. And that gives you the Largian behavior, so that this is not hard. You get this easily. Then you might think that you can also do this for the 1-2 entry, but it turns out that the direction of steepest descent is parallel to the real line, and somehow that it doesn't work. You can't pass the contour through this. Well, you can pass it through this, but you just can't apply steepest descent arguments. So there we have to do something a little bit more complicated. But essentially, what we can do is the following. So we can, we can pass the contour through 1, and then use that phi as a conformal map around SS1 and kind of invert it. And then you get an integral that's more or less this integral, not exactly. Where nu, I guess, has to be gamma over 2 plus 1. If you limit yourself to certain nice values of nu and w, then it's not that hard to show the following formula that you see here. So gamma infinity is some loop around the interval from 0 to infinity. And okay, and here you have the lower incomplete gamma function and the upper incomplete gamma function. But once you have this for these nice values of nu and w, actually you can use analytic continuation, and that shows that it actually holds for all values of nu and w. Okay. So let me then finish with some direction that we want to pursue. So as I told you before, Lee and Young also considered the case that the point insertion is outside of the droplet, or on the droplet boundary, or close to the droplet boundary. So this latter case is known as the double scaling regime. So here we don't only consider alpha of this form that you see here. I guess maybe this should have been C inverse minus 1. Okay, but you also consider x close to the droplet boundary. So in our case, that's it's close to square root c, and it has to be of order 1 over square root n. We expect to see some interesting behaviors there. We expect to see some Pain-Levé functions. But for now, we can't do that case. But what we could do, and what you will also find in the corresponding paper, is the case of weak non-unitarity. So in that case, we consider alpha to be constant. So the difference between the size of the unitary matrix and the truncation is considered to be constant. In that case, actually, so in that case, the droplet is actually the unit disk, and the correct scaling is of order 1 over n. And there we show that if you look at the moment of the characteristic polynomial, that you get a formula like this. You see over here, where here this sigma is a sigma Pain-Levé 5 type function. So it satisfies this Pain-Levé equation here. There are also certain boundary conditions that depend on alpha and gamma, but I'm omitting them over here. But so in the future we hope to be able to analyze this situation here, the first situation. Okay, that's all I have to say. So thanks for your attention.